Good morning, everyone, and welcome. I'm delighted to have you here today. Today's presentation is titled Management of GC Columns, and I'm excited to guide you through this important topic. We'll be covering key aspects of GC column management, including best practices and troubleshooting tips. So let's get started and explore how to optimize the performance of our gas chromatography columns. Let's start by talking about the GC column, which is really the heart of the entire gas chromatography process. It's the core component responsible for the separation of the different compounds in your sample. The quality of this separation depends heavily on the column itself, as it determines key aspects like resolution, selectivity, efficiency, and even how long your analysis takes. Basically, the column's performance directly influences the sensitivity of your detection, the shape of your peaks, and how stable your retention times are over multiple runs. If your column isn't performing well, it can lead to inconsistent results or missed detections. That's why proper column management is so crucial. It not only helps improve the robustness of your method, but also extends the lifetime of your column. Maintaining your GC column properly ensures reliable, accurate results and makes your analyses more efficient and reproducible. This ties right into the overall goal of achieving high-quality, dependable analytical data. Let's talk about how GC columns are constructed. First, the column tubing. The most common material here is fused silica, which offers excellent flexibility and chemical resistance. However, metal tubing, like stainless steel or MXD, is also used, especially when higher pressure or durability is needed. Moving on to the stationary phase, it's usually a polymer coating applied to the inner wall of the tube. This coating is crucial because it interacts with the analytes, helping us separate different compounds effectively. The film thickness can vary from about 0.1 to 5 micrometers, depending on what kind of separation we need. Now, regarding the dimensions of the column itself, typical lengths range from 10 to 60 meters. Longer columns can provide better separation, but they also increase analysis time. The internal diameter usually falls between 0.1 and 0.53 millimeters, which influences the resolution and sensitivity of the analysis. Finally, to protect the fused silica from damage and to improve durability, a polyimide coating is applied around the outer surface. This coating helps prevent breakage and makes handling easier, ensuring the column remains reliable throughout its use. All these design choices, materials, dimensions, coatings, are made to optimize the performance of the GC system and ensure accurate, efficient separations. Let's take a closer look at the different types of GC columns. First, we have nonpolar columns, which are typically made from 100% dimethyl polysiloxane. These are great for separating nonpolar compounds because they have minimal interactions with the analytes, allowing for faster and more straightforward separations. Next, there's the midpolar category, which uses 5 to 50% phenyl polysiloxane. These columns strike a balance, making them versatile for a wide range of compounds that have moderate polarity. They're often used when you need a bit more selectivity without sacrificing too much speed. Moving on to polar columns, such as those made with polyethylene glycol, also known as wax. These are ideal when you're analyzing very polar compounds, as they interact more strongly with those analytes, providing better separation for things like alcohols, acids, or sugars. Now, beyond these general types, there are specialty columns designed for specific applications. For example, pesticide analysis often requires columns tailored to separate complex mixtures of pesticides effectively. Similarly, VOCs, or volatile organic compounds, need columns optimized for rapid and sensitive detection. FAME, or fatty acid methyl esters, columns are specialized for lipid analysis, providing excellent resolution for these compounds. And then, we have chiral GC columns, which are unique because they can separate enantiomers, mirror image molecules that are otherwise identical but have different biological activities. Understanding these different column types is crucial because selecting the right one directly impacts the effectiveness and accuracy of our analysis, aligning with the overall goal of achieving precise and reliable results in chromatography. Let's take a closer look at how we select the right GC column for our analysis. First, we need to consider the analyte's volatility and polarity, because these factors influence which stationary phase will provide the best separation. Next, the boiling point range of our analytes is important. They help us determine whether the column can handle the temperature range needed without degradation. Another critical aspect is the resolution and selectivity required for our analysis. Depending on how complex our sample is, we might need a column that offers higher resolution to separate closely related compounds. Along with that, we need to be aware of the temperature limits of the stationary phase to avoid damage and ensure optimal performance. Detector compatibility is also key. Whether we're using FID, TCD, or MS, each detector has specific requirements that our column must meet. Now, looking at the column parameters themselves, the length of the column affects resolution. The longer the column, generally, the better the separation. The internal diameter, or ID, influences sensitivity, with narrower IDs typically providing higher sensitivity. And finally, the film thickness impacts capacity, meaning how much sample the column can handle without losing separation efficiency. Connecting all these points, remember that choosing the right column is about balancing these factors to match your specific analytical needs. It's a fundamental step that ensures accurate, reliable results in your chromatographic analysis. Now, let's talk about the installation and conditioning of the column. First, it's important to cut the column ends cleanly, and I recommend using a ceramic cutter for a precise, smooth cut. This helps ensure a proper seal and optimal performance. Next, when installing the column, make sure to insert it to the correct depth in both the inlet and the detector. Proper insertion is crucial for accurate sample transfer and consistent results. After installation, always check for leaks. Even small leaks can significantly affect your analysis, so take the time to verify everything is sealed properly. Moving on to conditioning the column, start by turning on the carrier gas flow. This is essential to begin the stabilization process. Then, gradually increase the oven temperature according to your method's requirements. It's very important not to inject any samples during this conditioning phase, as the goal here is to remove contaminants and stabilize the baseline. This process helps the column reach its optimal performance state, ensuring reliable and reproducible results for your analyses. Now, let's talk about carrier gas management, which is a crucial part of maintaining optimal chromatography performance. Common carrier gases include helium, hydrogen, and nitrogen. Each of these gases has its advantages, but the key is to always use high-purity gases, ideally with a purity of 99.999% or higher, to prevent contamination and ensure accurate results. It's also important to install oxygen and moisture traps in your system. These traps help remove any residual oxygen or moisture that could otherwise interfere with your analysis or damage your column. Additionally, maintaining the correct flow rate and linear velocity of the carrier gas is vital. Proper flow rates ensure that your separation is efficient and reproducible. And remember, exposure to oxygen can significantly shorten the lifespan of your column, so minimizing oxygen contact is essential for longevity. Overall, careful management of your carrier gases not only improves your data quality, but also extends the life of your equipment, tying back to our overall goal of reliable and cost-effective analysis. Let's talk about temperature programming. The key idea here is to start with the oven temperature set below the analyte's boiling point. This helps to prevent early loss of the analyte and ensures better separation right from the start. As the analysis progresses, we use a controlled temperature ramp to gradually increase the temperature. This controlled ramp improves the separation of components, making it easier to distinguish between different analytes. It's also important to remember not to exceed the maximum temperature specified for your column. Overheating can damage the column and compromise your results. When setting your temperature program, you need to choose an appropriate ramp rate, which is measured in degrees Celsius per minute. A rate that's too fast might cause poor separation, while one that's too slow can extend your run time unnecessarily. Don't forget to include a final hold time at the end of your temperature program. This helps to ensure that all analytes are fully eluted and that your results are consistent. Improper temperature control, such as sudden temperature changes or exceeding temperature limits, can cause column bleed. This is when the stationary phase degrades or contaminates the system, leading to poor data quality and potential damage. So, in summary, careful temperature programming, starting below the analyte's boiling point, controlling the ramp rate, and setting a proper final hold, are crucial steps to achieve reliable, high-quality results in your chromatography analysis. When handling and protecting your chromatography column, always remember to use a guard column or retention gap. These act as a first line of defense, helping to prolong the life of your main column. It's also crucial to avoid exposing the column to air at high temperatures, as this can cause damage or degradation of the stationary phase. Never touch the ends of the column with your bare hands to prevent contamination or physical damage, and always cap the ends during storage to keep them clean and protected. Additionally, make sure to prevent backflow of air into a hot column, since this can disrupt the separation process and harm the column. Now, moving on to sample injection best practices. You have different injection modes to choose from: split, splitless, and on-column. Selecting the right mode depends on your sample and analytical needs. Be cautious not to overload the column. Overloading can lead to poor separation and reproducibility issues. Always use clean solvents and vials to avoid introducing contaminants that could interfere with your analysis. Proper liner selection is also key. Using the right liner can significantly reduce contamination and improve your results. Remember, non-volatile residues can damage the stationary phase over time, so maintaining cleanliness and proper handling is essential for optimal performance and longevity of your column. Now, let's move on to column cleaning and maintenance, which is crucial for ensuring reliable and consistent results. First, it's important to regularly trim the contaminated end of the column inlet. This helps prevent buildup that can interfere with the separation process. Next, we have the bake-out procedure, where we increase the oven temperature under a stream of carrier gas. This step effectively removes residual contaminants from the column. It's also essential to replace septa and liners regularly. Over time, these components can degrade or become contaminated, which can compromise the integrity of your analysis. Keeping the injector clean is equally important. Regular cleaning prevents column contamination that could lead to poor separation or signal issues. And a key point to remember: avoid using solvents to wash capillary columns. Solvents can leave residues or damage the delicate coating inside the column, so stick to proper cleaning protocols. Overall, diligent maintenance and timely cleaning are fundamental to maintaining optimal column performance and ensuring the accuracy of your results. Now, let's look at some essential guidelines for storing columns properly. First, it's best to keep the columns at room temperature. This helps maintain their stability and prevents any temperature-related degradation. Next, it's important to seal the ends with caps. This simple step prevents contamination and keeps the column's interior protected. If possible, storing the column under an inert gas like nitrogen can offer extra protection, especially for sensitive samples. We also want to avoid humid and dusty environments, as these conditions can negatively impact the column's performance and longevity. And finally, it's crucial to keep detailed records. Make sure to note the type of column you're using, its usage history, and the maximum temperature it has been exposed to. Keeping track of this information helps ensure optimal performance and informs future handling. Overall, these guidelines are key to preserving the integrity of your columns and ensuring reliable results in your experiments. Let's now talk about some common problems you might encounter with GC columns. One issue is high column bleed, which can cause baseline noise and interfere with your detection sensitivity. Peak tailing is another common problem, where peaks become asymmetric, making it harder to accurately quantify compounds. Loss of resolution is also critical, as it can lead to overlapping peaks and misidentification of analytes. Ghost peaks, these unexpected signals, can sometimes appear due to contaminants or carryover, complicating your analysis. Retention time drift is also something to watch out for, as it can affect the reproducibility and reliability of your results. To keep everything running smoothly, monitoring column performance is essential. You want to keep an eye on key indicators like retention time stability, which tells you if your system is consistent over time. Peak shape and symmetry are also important, as they reflect the column's health and performance. Resolution between critical pairs is crucial for separating closely related compounds effectively. Additionally, observing column bleed, which can show up as baseline rise, helps you catch issues early. And remember, system suitability tests are a vital part of quality control. They ensure your system performs as expected before you run your samples. Keeping a close eye on these factors helps maintain reliable, accurate results in your chromatography work. Let's take a look at some common causes of issues and the best ways to address them. First up is oxygen damage. When oxygen gets into the system, it can cause deterioration, so the best solution here is to replace the column to restore proper function. Next, contamination is a frequent problem, which can lead to poor performance. The fix for this is to trim the column, removing the contaminated sections. Overheating is another cause we often see. If the system is running too hot, lowering the maximum temperature can prevent damage and ensure stability. Lastly, poor installation can lead to a variety of problems. The key here is to reinstall the components correctly, following proper procedures to avoid future issues. Recognizing these common causes and applying the right solutions is crucial for maintaining system health and performance, tying back to our overall goal of ensuring reliability and efficiency. So, to wrap things up, the key takeaway is that proper GC column use is absolutely essential for ensuring reliable results in our analyses. When we handle our columns correctly, we can trust the data we get and make better informed decisions. Preventive maintenance plays a big role here too. It's not just about fixing things when they break, but actively taking steps to extend the life of our columns. This saves us time and money in the long run and keeps our instruments running smoothly. And finally, managing our columns properly helps us reduce downtime and cut costs. When we stay on top of maintenance and best practices, we minimize interruptions and avoid expensive repairs or replacements. Overall, these points tie back to the core theme of maintaining high-quality, efficient analytical workflows. It's about being proactive and meticulous, so our results are always accurate and our operations are as cost-effective as possible. For further support, please don't hesitate to reach out to us. We're here to help you with any questions or additional information you might need after this presentation. Thank you so much for your time and attention today. We appreciate your interest and look forward to connecting with you soon.